Anupam, are you there?
Yeah.
Can you?
Okay.
Excellent. Okay, then let's start with the first talk. Before we start, let me remind everybody that if you have questions, you can write them in this chat box at the bottom in Zoom, and I will try to read them out to Anupam. And so we start with this talk, which is a survey about chasing convex bodies, which was an open problem for quite some time, but so there have been kind of significant advances recently, and the talk will be given by Anupam Gupta.
Great. Thanks, Matthias. Thanks, everybody, and sorry for being slightly late. So I'll be talking about a bunch of work that a group of people have been doing on chasing convex bodies, and this is based on slides by my student CJ. So without further ado, let me just start. So the problem is very simply stated. There's a d-dimensional convex space, and the algorithm controls the point. And now at each point in time, a convex body arrives. And once you move the algorithm, the only thing it can do is it can move the point to within the convex body. And it pays the distance. Okay. And then another convex body arrives, and then the algorithm moves the point, and then you get the idea. At each point in time, convex body, algorithm moves the point, pays the distance, and the algorithm's cost is the sum of all these distances. And then the question is, well, of course, this is an online problem, and so the standard model we consider is comparative analysis, that we look in hindsight at the instance received, and then we can say what was the best way of handling this instance, and that's opt. And in this case, you'll notice that opt in the second step moves to a point where it can handle both the second request and the third request. So it can be smart about it. But of course, it has to handle the requests in the same order, naturally. And the comparative ratio is, as usual, the ratio between the algorithm's cost and the optimum cost. And you look at the worst case and you ask yourself, what is the comparative ratio? And this is the question that Friedman and Lindell asked in '94 when they first proposed the problem. So the problem comes in many variants, and I'll just mention two variants just to get us started. So the first variant is the nested one, where the bodies are going to be nested. So the second body is going to be contained in the first one, and the third one, so on and so forth. And in this case, there is one observation that you can make immediately, is that the right thing to do is to move from the original point to its closest point in the final body. So you just project on the original point onto the final body, and that's the right solution. By the way, I haven't mentioned the norm I'm using here is the Euclidean norm. You can consider this for other norms. It's interesting as well, but I'm not going to focus on that right now. I'll mention something towards the end. So this nested version was considered by Bunsell and others in a Soda paper in 2018. It's a simpler case, and you might want to start from there. So we will start from there, and we'll see that ideas from this nested case generalized to the full case. So that's the model. If you have any questions, please do ask anytime, and Matthias will do me the favor of translating them. Good. Okay. So if the problem is clear, maybe there is a question, and
so how do you know the last convex body? I mean, I guess
no. So as in comparative analysis, you imagine that you keep on going, and then at some point the adversary says, "Okay, let's see what you've got." So this is, you can imagine this as being a worst case over all possible times as well. So I'm imagining that I'm doing the comparative analysis at some point in the input sequence. Okay. So given this, let me just mention one problem, which is a slight generalization of this. It's called convex function chasing. And so what's the difference? at each point in time, a convex function arrives. So in this case, I'm controlling a point in, let me use a different color. I'm controlling a point in one-dimensional space. And so the function is defined on the one-dimensional space. And now, if I control this point and this function arrives, I can move it to some other point, let's say, and call this x1. And at this point, I'll pay the distance I moved plus the function value at this point. And then another function arrives, and then I might decide to move my point to some other place and take the function at that point. And this might be x2. Okay? So you pay both the distance cost and the function cost. And those of you who've been sort of looking at developments in online convex optimization, you will see that the difference is really that we are paying for the change. In online convex optimization, you pay for the function cost, you don't pay for the distance cost. But there are other changes. Out there, you don't see the function before you play the point and other things. But this is a very natural question. I have a, yeah, good. So this was also proposed by the same original paper. And it turns out, and I'll maybe mention this very quickly, that it turns out that you can reduce the problems to each other. And maybe I'll mention this at the end, but okay, so let me just tell you how to reduce the problems to each other. If anything else, you'll get this proof right off the bat. So what I'll do is I'll reduce function chasing to body chasing in one higher dimension. So remember, these functions were in one-dimensional space. So I'll imagine the first instance, the first request to be this body. So you have to move into this point. Now I'll throw in a random, a different request, which is the original space. So you have to move back. And then I'll give you the next convex body, which is this one. So you might have to move up there or something like this. And you can see, this is almost the same picture I drew on the previous one up to Pythagoras, right? So, so you can do this translation and you can get within constants. So whatever you get for functions, you can get for bodies trivially, because you can take the indicator of the body, and whatever you get for bodies, you get for functions in one dimension. So the two problems are similar. Okay, good. Okay, why do we care about this problem? Well, maybe I won't mention too much of the applications, but basically it's a vast generalization of a lot of online problems that we have been studying over time, paging, k-server, metrical task systems. And you should really think of this as like a generic online convex optimization. And we're asking ourselves, what kind of techniques can we develop? What can we do in this generality? And once we have such a general thing, we can solve a whole bunch of problems, maybe not optimally, then we can optimize these things. So it gives us a framework. We want to develop a robust general framework. And it also comes up very naturally, especially the function chasing problem. It comes up very naturally in many different applications. So for instance, Adam Weirman's group at Caltech has been studying this from the perspective of trying to make the optimal decisions in data center energy usage. Yeah. So there's many reasons. There's of course one very good reason. It's a beautiful, simple problem. It has convex functions in it, or convex bodies in it. It has online algorithms in it. What's not to like? So that's all I'm going to say about the motivation. And let me tell you a little bit about the history. It was introduced in this paper by Friedman and Linnell, who gave two algorithms. An algorithm for chasing lines in the plane. So at each point, we're working in R2, and at each point in time, a line arrives, and you've got to move to that line. And then another line arrives, and you've got to move to that line. And then they extended this to convex body in the plane as well. And it's a non-trivial algorithm. So I'm not going to talk about either of these things. They gave a lower bound, and the lower bound is kind of useful to understand. So let me just give you the lower bound. So basically, I'll tell you that one of the corners of this cube are going to be the final point. I'm going to give you a nested instance. And eventually, I'm going to make you move to one of the corners of the cube. So you are at the center. And now I give you this face. So where should you move? You don't know whether the final answer is going to be at the top or the bottom. So chances are, you should move to the middle. This is the right thing to do. You can show that. And then, of course, now I'll give you one of the endpoints, and you'll have to move to that endpoint. And so you paid the 2 dimensions, whereas you should have paid the hypotenuse. So again, Pythagoras makes you lose the square root of d, the square root of 2 in 2 dimensions, square root of d. And this gives you a sense that, the nested body is like square root of d far away. The nested body chasing problem is square root of d far away from being solvable. But maybe we can do square root of d comparative analysis, comparative ratio. Okay, we good with this? So yeah, one annoyance with, as with teaching all the time, one annoyance is I can never really see what people are seeing. So, but it's okay.
So let me help by asking,
please.
Well, reading out a question really. What is the role of convexity? So
good. So if you don't have convexity, more or less, I can give you 2 disjoint pieces, and I can say, you should be here or you should be there. And you can construct really bad examples. And in fact, this is being considered later on. Without convexity, you won't be able to localize the point. You may not be able to localize the point. Convexity gives you a lot of power. If I keep giving you 2 points, convexity allows you to say, oh, you can sit in the middle. And that might help you.
So there's kind of a second part to that question that I'm not so there's forgetting about convex optimization
right
at the moment. What about CBC or CFC themselves?
Right.
But I'm not, what is CBC or CFC? I'm not.
So CBC is convex body chasing, CFC is convex function chasing.
Oh, I see. Okay.
I snuck in the.
Okay. I think you answered that, right? Yeah.
Okay, good. Yeah, I mean, otherwise, yeah, okay. Let me move on.
To slow you down even more, so does the hardness remain the same when you have more nested polygons instead of 2?
More nested polygons. So the square root of d is going to come from actually d-nested polygons. I'll give you initially the d-dimensional cube, then I'll give you a facet of that, then I'll give you a low-dimensional face, and so on and so forth. So, but to answer sort of a deeper question, it does remain the same, as we will see in the talk, right? Or more or less the same. At least that's what we know. Okay. They made a simple reduction, which is also useful to note. They say that, look, if you can chase half spaces, then you can chase any convex bodies. And those of us who have heard of or seen the ellipsoid algorithm, it's, this is no surprise, right? If I want to chase this body, then I can first give you a separating hyperplane. You move. If you didn't get inside the body, I can give you another separating hyperplane. You move, and so on and so forth. Right? So using the Han-Banach theorem or whatever, separating hyperplane theorem, the 2 problems are equivalent to each other. Good. And then they made this conjecture that for any d, the set of closed convex sets in metric space Rd is chaseable, as in there is some finite comparative ratio which is just a function of d.
So one more question to read out, and I probably should have maybe acknowledged who is asking the question for the purposes of the recording, but I apologize to the 3 people before. So Karthik asked, is chasing equal getting a square root n competitive ratio? I mean, like, so if it's chaseable, is it competitive?
So basically, chaseable is just their shorthand for saying there is a comparative ratio which is independent of everything else, only dependent on the dimension.
Right.
Perfect. Good. Yeah, there is some amount of jargon, so do slow me down. I'm happy to. This. Okay. So what's the rest of the talk? I'll give you some general clean algorithms, some nice connections to convex geometry. And part of this is I've been learning some of this stuff myself, so I'm eager to tell you all about it. Okay, so more concretely, the roadmap is going to be, I'll prove the conjecture to you, more or less. I'm going to first cast a simpler version of the problem, which is not really simpler, it's the equivalent. I'll give you a couple of algorithms that will fail, maybe give you some intuition. Then we'll talk about the nested case and the general case. And then if time permits, which it probably won't, I'll tell you some other stuff. Okay, so here's the simpler case. The convex bodies are all going to be in some R ball, some radius R ball. So the initial body is going to be this ball, and you're sitting at the center. And then I'll give you a body, some body inside there, then another body inside there, and so on and so forth. I promise you that opt is going to pay no more than R. Okay? And I want you to pay R times some function of t. Okay? So opt pays R, you pay R times some function of t. And this is equivalent to the original body by just the simple idea of guess and double. If you haven't seen this before, that's another day. Just think of this simpler case that I want to solve. R ball, bodies come in there, you chase them, you're guaranteed that opt is no more than R. Okay, good. So here's an algorithm, which actually doesn't depend on the guess and double, but I just wanted to get guess and double out of the way. Okay, so here's the simplest algorithm you might try. Move to the closest point. I give you a body, project, move to project. Greedily, you're making the best decision at this time, right? But of course, even this example is showing you where you would go wrong, right? I could give you these half spaces, which will make you go around almost in the spiral-like thing. Whereas what's the right thing to do in hindsight? Just move to the center. So once I start seeing all these guys, you should have realized, I'm making you go around in a circle. You should move to the center. So this somehow indicates, look, greedy strategies. In general, memory-less strategies are tricky. You should be a little careful. Okay. Now you might say, and I'm not going to give you a picture for this, how about at each point in time, I figure out the optimum for the sequence I've seen so far. This is just a convex program. Move to that point. In the jargon of online convex optimization, this is called follow the leader. Follow the leader, also crappy algorithm. Okay? Simple examples, another day. Okay? Here's a different one. For the nested point, for the nested body, and this is a sort of an interesting thing. You know that this body starts off as being the ball and it's going to get shaved away over time. You don't want to move too often. So what's a good way of doing this? Move to the center of the body. So when you move to the center of the body, and now if you have to move next time, then the center is no longer in the body anymore. So the body has lost half of its body, whatever it means. Actually, formally, you can use a theorem due to Bruno Grunbaum that basically, if you cut off the centroid of the body, this is the center of mass. There's so many centers of convex bodies, it gets confusing, but this is the center of mass or center of gravity or the barycenter, 100 names for this. Okay, center of mass. So if you cut off the center of mass via a half space, the volume decreases by a constant factor. Beautiful, simple idea. And I'm using convexity crucially out here. Okay? So every time I move, half my volume decreases. Well, this is great, right? The volume is dropping so rapidly. Good things should be happening. Okay? Now, sadly, volume does not equal distance, right? If the body always remained like kind of well-rounded, we'd be fine. But what happens is, here's an example. I'm sitting at the center of this body, which was initially the center of mass. I shave it off. Now, I have to move. But see, the way I cut it off at an angle. So the center of mass not only has moved downwards, but it has also moved to the right. Okay? And then I center you back. And then I shave it off a little more and I make you move. And you see, each time I'll make you move a little bit down, but a lot to the right. And then back, and then back, and then back. And you're kind of zigzagging like this, whereas you see what the right thing to do is, but this algorithm is not doing it. Okay? And this, the algorithm can be unbounded. And actually, this was in the paper of Nikhil Bansal and others, and we also noticed it. I mean, it's no rocket science out here, not competitive. Okay? But actually, what would you do if you saw this thing? Right? After a little while, this body has become like a pancake. It's become like very slim in one dimension. So if it's like a pancake, why do you worry about the thin direction? Only worry about the fat directions. Okay, so let me give you a picture. I took this ball and I kept shaving it off until it becomes like this pancake down there. If it's a pancake, really you should kind of project out the thin direction and only work on the fat directions. Okay, and in fact, this is an algorithm we called recursive centroid. This is a paper with CJ, Sebastian Bubeck, Michael Cohen, and Yin-Tat Lee. And we showed that, look, keep doing this until there's some directions which are slim. Then kind of project them out and just work on the fat directions. And I'm not expecting you to get all the details, but really there is still distance in the thin directions. An optimal solution, even if my body kind of looks like this, I don't want to make sure I don't want to spend too much time on this side. So I have to be a little careful, but I can control the amount of movement I do in the thin directions. And loosely, here's the thing you should keep in mind. A thin direction is one which has width less than 1 over poly d of the radius. So if I keep cutting volume, I need about log d many steps to get a thin direction. So what can happen is I start off with a ball, the adversary shaves off this body until it becomes a pancake. I've lost one direction, it took log n steps. There are d directions to lose. If everything worked out fine, I would pay d times log d to reduce the body to like a tiny mass, and then I'll be done. I don't know if I don't expect you to get all the details of this thing, but at least I want to get you the intuition. Okay. And this theorem just said, the recursive centroid algorithm is d log d competitive. It's a simple proof. It's there's a potential function, you use the volume, projecting from 3 dimensions to 2 dimensions actually increases the volume. But these cuts are decreasing it, and you play this delicate game. That's how you do it. Okay. And in fact, then Bubeck, Klartag, Lee, and Selke, paper at Soda this year, showed that, look, you are moving in Euclidean norm. So maybe you can measure distances, you can measure volume in a way that's more conducive to the geometry of this problem. And it's a very, very clever idea that they use Gaussian volume instead of regular volume to be able to show that, it dampens the movement a little bit, and you actually get square root d log d comparative, which is within like square root of log d of the correct answer. You remember the square root d lower bound earlier? So this is within log factors of the square root d. So this really, for the nested version of the problem, it really nails it. We know exactly, well, not exactly. We pretty much know what the right answer is. And it's a very nice algorithm. I really like it. Good. And so, of course, the question was, we've solved the nested case. We hope that the nested case would give us intuition about the general case. How do we solve the general case? And breakthrough, Sebastian Bubeck, Yintat Li, Yuanji Li, and Mark Selke in Stock showed that there is a fair extension of the recursive centroid algorithm that I kind of sketched, which is 2 to the order d competitive. It's complicated. It's not quite an algorithm that I could explain to you and explain other things right now. It would take me a little time to explain it. So maybe I'll leave you with a picture like this. Yeah. Zero knowledge proofs, right? Proof by intimidation. This proof exists. But it's a very nice paper. If you are interested in this stuff, I urge you to look at it. And it tries to estimate where should opt be, and then it kind of runs a recursive centroid on that body. Anyways, another day, maybe over drinks afterwards. But maybe I should stop for a second and ask for if there are any questions. I've been trundling along, so.
I don't see any yet, but I'm happy to interrupt you if there are some.
Yeah, no. I mean, sometimes, I just started teaching yesterday, so I'm in this mode where I'm anxious for questions right now. By the end of the semester, I might be sick of them, but that's okay. It's okay. Good.
Yeah. If something is there is something.
There is one. Victory.
Eklavia Sharma asked, instead of shaving off a large fraction of the body, if the adversary almost keeps it the same,
right,
then the optimal thing to do would be to move to a nearest point in the body. But the centroid algorithm would move to the center, which could be very far.
Right. See, the thing is that this is why I reduced the problem to this bounded version. You remember? I said, I know what opt is. Opt is about R. And you can pay f of d times R. So I've already kind of guessed that the right scale is R. So I can afford to move to the center of the body.
And Fabrizio asked whether there are better lower bounds for the general non-nested case, but I'm guessing you will get to that eventually.
Yeah, no, I can answer the question right away. Yeah. No.
Okay.
So in we can beat the square root 2 for chasing, to 1.5 something. But the square root d essentially remains unchanged. I don't know of a lower bound better than that. I'd love a better lower bound. Okay. Good. So let me then get into the rest of the talk. Matthias, do you want to butt in with the last question? You okay?
No, I think we're fine.
Okay, good. Okay, so this idea of keep an estimate of where opt might be is a useful thing. We'll come back to this. Okay, So the result I'll tell you about is two papers actually. I'm going to talk more about the work that we did because I know it better. So this is a paper with CJ Argue. This is a grad student with me, Guru Gurganesh, who was a grad student with me, and Jie Tang, who is a grad student in the Tepper School. And Mark Selker's paper, and both of them appeared at the SODA conference this year. Okay. And basically, in a nutshell, I'll show you a decompetitive algorithm, which is, I call the work function Steiner point algorithm. I don't expect you to know what work function is or Steiner point is, but I'll explain both of these things. Okay. And it's decompetitive and it's fairly simple, and it's got some nice new ideas. Okay, good. So I'll give you the algorithm in three pieces. So remember, there were two terms in the previous slide. I haven't defined work function, Steiner point. But in order to define the Steiner point, I need to tell you what the support function of a convex body is. It's like a trivial idea, but I'll tell you first. Then I'll define the Steiner point. And then using this, I'll give you a new algorithm for nested convex bodies. And then I'll define the work function, which those of you who work in online algorithms is known for a long time. And using this, I'll give you the algorithm for the general case. Okay. Good. Okay, so let's start off. Now let's roll up our sleeves and get down to business. So the support function of a convex body is this very simple idea. The function takes in an argument theta, and there's a convex body K. So this blue box out here, and it just maximizes the linear function with objective, defined by theta over this convex body. Okay. So what is the hk of theta for this? You'll take the inner product of these two vectors. Okay. If the vector, okay. Ignore that for a second. Just let me just define it. So it turns out, so this is a convex function, and it turns out that if you take the gradient of this convex function, remember the gradient is this high dimensional derivative, right? The gradient is just the maximizing point out there, actually. So it turns out that the gradient of hk of theta for this theta is this point. Okay, this is just a definition. So let's just make sure. If I change theta, hk of theta moves to that point. If I change this theta, nothing really changed because the maximizing, the corner in that direction remains the same. If I change it there, it moves there. And always the support function value is just the inner product of these two vectors. Okay, it's just, it's just a fact. Perhaps this is the one that you should remember, and this is just, this is helping you define this object. Okay, this is the support function and its gradient. No big deal. It's a definition. Good. We're done with 1/3 of the rest of the talk. So the remaining 2/3 now. Right? Okay. So let's define the Steiner point. So the Steiner point is a notion of a center of a convex body, and it's like a stable center. So there's a history associated with this, and there's this very nice short survey by Benjamin Lind and Strauss that you could look at. There's this big book by Schneider. Anyways, so what's the Steiner point? Let me just define it. So the Steiner point says, pick a random direction, random theta, okay? And look at the extreme point in that direction. Okay, gives you a point, average it out. That's the Steiner point of this body. Okay. So if I gave you, let's say, a polyhedral body, then it's easier to understand. And let me just move this. Sorry. Okay. Sorry. Yeah. So what's it? Basically, if you look at all the extreme points and you look at the normal cone, I mean, the normal cone is defined as exactly those directions, which will give you this point as the maximizer, right? So it's the average of the extreme points weighted by the volume of the normal cone at that point. There's a tiny little normal cone on, for this guy. There's a bigger normal cone for this guy. But it is what it is, right? I know that phrase has become laden with political significance nowadays, but we're mathematics talk, so it's all right. Okay, so this is the Steiner point. And this picture, if there's one picture to keep in mind, actually both these pictures are very useful. This picture that just look at the corners, look at the volumes of those guys, and average according to that weighting. This is the Steiner point. Okay, good. And the Steiner point, okay, so what's the Steiner point? So remember, please.
So there's a question from Deepana, saying which volume is this? Is it Gaussian volume? Or?
Oh, no, so I'm just working with the usual notion of volume, the Lebesgue measure or whatever. Yeah. Standard volume, no fanciness going on. Good point. Okay. Good. But actually, sort of in this case, if I'm looking at you'll see that in this case, because of the spherical symmetry, because I'm taking the average, I could have chosen a random Gaussian as well. It won't really matter. What did I do? I picked a random direction. So I can take the Haar measure over the surface of the sphere. Or I can pick a random Gaussian with the identity covariance matrix. It's the same thing because it's spherically symmetric. So maybe I should clarify that it doesn't matter. Okay. So okay, this is a Steiner point. Remember, this is the maximizing point, right? In the direction of theta. So the Steiner point is really the average over all possible points. It's just this integral of the maximizing point in that direction. That's just the definition. Restated. Which is, I can write this as an expectation like this, which I will again and again. And maybe let me just recast it and just say what I just, I mentioned a second ago. Instead of picking a unit vector from the surface of the sphere, I could pick a Gaussian with with each coordinate is an independent unit normal. It's also spherically symmetric. So it's the same thing. And then I can write this as this object out here. What have I done? This is the maximizing point, and this is just the density function out here. This is just the definition of the integral. Nothing's happening here. I just want you to, just say I'm just doing, algebraic manipulations out here. Okay, why am I doing all this? Okay, why I'm doing this is because we need to understand the Steiner point a little more. Okay, so the Steiner point, as I said, is the expected extreme point for a random G. G will always stand for Gaussian, by the way. From now on, I'm just picking a random Gaussian, maximizing in that direction, and that's the value. That's the Steiner point. Okay, good. And now I'm going to claim that it's equal to this other object. Okay, what is this other object? Let me just parse that. Let me unpackage this for you. This is a vector. This is the random Gaussian that we picked. This is a scalar. This is the support function value. This is the inner product between the Gaussian and this and the maximizing point. Okay, and my claim is that these two definitions are the same. And this thing is at the heart of all usages of the Steiner point that I know. I'm sure there are others that I don't know. And normally this is proved using Stokes' theorem or the divergence theorem or something like this stuff that I was taught when I was an undergrad, and I kicked and screamed and I didn't learn it, and I still whistle nervously when I have to deal with these things. But actually, I'll show you a proof of this equality in just a moment. Okay. So why am I telling you all this? The top one is visually intuitive. It's just this picture on the right. And it's a proof that the Steiner point lies inside the body. The bottom one is algebraically useful. But I don't know of a simple proof that that definition gives you a point inside the body. Okay? But that will be algebraically useful, and maybe I'll flash a slide on this thing, but let's not worry. Okay? So let me show you this equivalence, and this equivalence is actually, yeah. So I want to show this. And if you don't feel like seeing any algebra right now, but this is a cool trick. Actually, you should see this one. Okay, let's prove it for a one-dimensional case. So what's the one-dimensional case? The left side is just a derivative. That's just that, right? It's the expectation, it's the integral over f prime of x, mu x dx, where mu is the density of the Gaussian. The right side, you'll notice, has only an f, and this is an f prime. Do we have suggestions on what to use now? You should use the integration by parts. So if you use integration by parts, you'll get this. I mean, you look up Wikipedia, right? I mean, or just think back to your calculus days. It's just this. It moves the prime from there to there. It is a minus something something. These terms, because the Gaussian measure goes to 0 as at infinity. You can do this formally. You should take limits and stuff like this. These terms are 0. So you are left with this term, but the derivative of the Gaussian can be easily taken. And so if you do this, you get an x. Sorry, you get an x sitting there. You do the calculation, and you get the answer. And I don't expect you to expend your time checking my algebra. I want you to be convinced that you can prove it if you need it. It's just integration by parts. And this is really Gaussian integration by parts, a very simple case of that. And if you do this, and now you do this dimension by dimension, sort of conditionally, you just lift it to a higher dimension. It's not very difficult to show that. So this fact is, I want to show this fact. Okay, good. So what did I say? I said the Steiner point is defined as this beautiful object, and it has this algebraically useful derivation. And I'm running out of time, but using this, now I can show you a proof for nested convex bodies, an algorithm for nested convex bodies. And the algorithm is the easiest algorithm in the world to define. Forget all this. The algorithm is move to the Steiner point. Move to the centroid was a slight problem. Move to the Steiner point. Okay. And let me show you, let me try to convince you by example why this is a good thing. So let's go back to that bad example. Okay. Now remember, I'm not weighting my movement by the volume. I'm weighting it by the volume of these corners, right? Of these normal cones. So you'll move somewhere there. Look at how the two normal cones, these two normal cones, are kind of shifting in the obvious way. Okay. Now I come back, the normal cones are all balanced now. Now you give me something like this. the normal cones are shifted, but they're not quite as unbalanced as before, remember, because the body is, kind of slimmer. And so you'll move less. And this somehow shows that, it's not it's because it's taking care of the normal cones and not the volume. It's actually being kind of smart about things. It's still a magical algorithm. This algorithm due to Bubek, Clarta, Glili, and Selker. It's a magical algorithm. It's very similar to a previous proof about something Lipschitzness of the Hausdorff measure, whatever. Not important. See Benjamini, Lindenstrass. They'll give you some intuition for background. This algorithm, very simple. Okay. So it's a smoother version. It's decompetitive. In fact, it's decompetitive. It's just D. And it's memoryless. This goes to show, initially I thought there can't be a good memoryless algorithm for nested body chasing. How wrong I was. Okay. And the proof is one slide. I'm not going to go over this. You use linearity of expectation twice. You use the other definition of standard point, and it's elementary. I assure you it's elementary. I can share my slides. You can look at it later on. Let's not worry about it. It's late enough in my talk. I don't want to use up your energy in understanding this algebra. In fact, I'll use a quotation that a phrase that Asaf Naur once used. If you sit down to prove it, you cannot not prove it. It's like once you know all the ingredients, it's like follow your nose, pretty much.
So Neil Oliver asks if this is tight for this algorithm. So this D.
Good. Absolutely. So that's an excellent question. It is tight for this algorithm. However, one thing that comes out is in order to get a tight example, you need a request sequence which is exponentially long. So you can show that this algorithm is, okay, do me a favor and go where I want you to. Okay, can I get out of this mess? Let's just keep that. And sorry guys, something bad just happened. Okay. I was here, and let me share my screen again. Okay, so I'm not going to write anything because I'll break something, but the behavior is like D and square root of D log T, where T is a number of steps. Maybe square root. Okay, whatever. Okay, good. So final piece, and I have about 8 minutes or so. 8 minutes?
Yeah, pretty much.
Okay. So I'll tell you what the work function is. I'll give you an impressionistic view of what's happening. Almost, it's, yeah. Okay. The work function, very simple idea as well. Okay. The work function is a function of the request sequence, and it changes over time. So the work function at time t of a point x is the min cost way to handle the first t request and end up at x. Okay. So here are two examples. The first guy, if you wanted to handle both the requests and end up at that point, you just go straight there. Whereas if you wanted to end up at y, the best way would be to actually figure out how a ray of light would travel in that way. Okay, this is the work function. No rocket science really. The work function is, if I want to handle all the requests and end up at this point x, what should I do? How much should I pay? That's really the object. Okay? We good? So basically, remember I told you that opt pays no more than R. So where can opt be? opt can be at all the places where the work function is at most r. Right? These are all the points where you can reach by paying at most r and handling all the requests, of course. Okay? So opt is sitting somewhere inside this egg out here. I don't know where. And this egg is shrinking because opt has to pay more and more, right? Over time. Good. Oh, by the way, it is shrinking because the work function is monotone. So this shows you that this egg is nested. Each egg is contained in the previous egg. Okay. Already this is good. I'm chasing a nested. No, I'm getting ahead of myself. Okay. So another thing I can show is that this egg, this omega t. Okay, so I have defined omega t. I haven't told you guys. So omega t is the set of all points where the work function is at most r. This is all the places opt can be. This is a convex set, and you'll see convexity. If you could reach x and you could reach y, then you can reach their average. Okay, good. It's monotone. Come on, guys. Another request is not going to make the cheapest way cheaper. So it's nested. So here's what the idea. And several of us had this idea for some time. We didn't know how to make use of it. My instance is non-nested. These estimates are, however, nested. Why don't I chase these nested bodies? I have good algorithm for chasing nested bodies. But come on, guys. Chasing. All I know is that this omega t, this point that I'm chasing, is inside omega t. It's an estimate of where opt is. It's not inside the body I want to be. Are we good? We see a problem. I mean, we see the general idea, right? Okay. So here's my problem. I want to be inside K1, but I'm chasing omega 1. So my omega 1 algorithm says, go to that point. That's not feasible. So one thing I could do is I could go to K1 and then come back, right? But how much do I pay? How do I control what I pay? And in some sense, you can think of the 2 to the D algorithm as kind of controlling this in some very smart way. Okay. So the worry really is, I'm chasing omegas. Omegas might be infeasible. And the miracle is, well, the Steiner point is feasible. Okay. And let me show you like a picture. What's the picture? So, basically what I did was I took these Ks. These are ones I want to chase. I got estimates omegas. These are where opt might be. I moved to the Steiner point of these omegas. And hey, it's a miracle. Actually, this is feasible for K. What the heck? Right? So this is basically the algorithm, and the proof of feasibility is one picture. So let me imagine that I'm chasing a convex half plane. And let me define the notion. Okay, so what do I want to do? I want to be on the right side of this green line. And the notion of reflection is very easily defined. For a point, its reflection against this white line is where, its reflection. If a point is on the right-hand side, its reflection is itself. There's nothing like that. Okay, good. Okay. Omega is somewhere. I want to show that its Steiner point is to the right. Okay. Fact. I want to claim that take any point inside omega, its reflection is to the right. Oh, sorry, its reflection is inside omega. Of course, it's to the right. I mean, that's the definition of reflection, right? But it's inside omega. Okay. So, this case is trivial. So let's look at this case. I'm looking at the point y, its reflection y hat. And I'm saying, hey, if I can reach y paying at most r, then of course I can reach y hat paying at most r, right? So the reflection of the stuff outside stays within omega. But what's the Steiner point of omega? It's some notion of center, right? Omega consists of this stuff plus this junk. But this junk is all to the right. So any self-respecting notion of center must move the center more to the right than to the left if I add junk to the right, right? That's it. I mean, that's the proof. You can make this formal, but who cares? You know? Again, easy proof, but here's the proof. It's like 3 lines, whatever. So that's it, guys. The work function Steiner point algorithm is decompetitive. Let me just mention 2 other things. I'm pretty much at 0 time, but let me tell you a couple of things. Matthias, it's okay to do it?
Yeah, please do.
Okay. So this algorithm that the algorithm that I mentioned is in this paper with CJ, Guru, and GM. Mark's algorithm is essentially is slightly stronger in some sense. He defines the notion of a Steiner point for a convex function. And I'll show you the definitions. I don't have time to go into this thing. If you're given a convex function f, you look at the dual of that function. There's a certain dual called the Fenchel dual, and you look at its gradient. And if there's, if it helps you, I can take the indicator of a function. This is just the point. This is a function which is 0 inside the convex body and infinity outside. So for a convex body, I can talk about its indicator. And then if I look at the indicator's dual, actually it should be now theta, it's actually equal to the support function of theta. So all I'm saying is this definition generalizes the definition of a Steiner point directly. And it's a very natural definition. And using this, he actually gives an algorithm for convex function chasing, which is move to the Steiner point of the convex, of the work function. Move to the functional Steiner point of the work function. You don't need guess and double. It works for all norms. In fact, his proof shows that our algorithm works for all norms as well, but our proof does not show that. So his proof is stronger in that sense. And it's a general unified view. If you're interested, have a look at his paper. It's short and sweet. Okay. Couple of other directions I'll mention. You can talk about chasing lines. So in general, chasing subspaces. And in some recent work, we showed that you can actually reduce chasing k-dimensional affine subspaces to order k-dimensional chasing of general bodies. So you can get order k competitive algorithms. Order square root k is the best you can do. Not clear what else to do about this. But it would be nice to get tight algorithms for these things. So in general, a tight algorithm for all these questions remains open. Multi-server chasing. It's like k-server. You control 2 points. I'll give you a convex body. Move either of these points inside the convex body. Actually, if you have 2 servers and 2 dimensions, you're already dead. So there's this paper of Sebastian Yuval Rabani and Mark Selka that shows that this is not doable. You can talk about chasing nice functions which have good condition numbers. And this is a line of work that people have been interested in for some time. And you can show something nice about this. Again, gaps all over. But instead of spending too much time on that, maybe I'll just wrap up. you saw a d-dimensional convex, you saw a d-competitive algorithm for d-dimensional convex body chasing. You heard about one which is square root d log d for nested convex bodies. And you saw a square root d log 1. There's a very natural gap out here. Somebody should close it. Yeah. Either an upper bound or a lower bound. Both are interesting. What can you do for nice convex bodies? So for a lot of our problems that we care about, like K-server paging, the instance looks like this. I'll give you a base polytope. I'll give you, not by base, I mean, I give you a fixed polytope, and each time I'll ask you for a facet of this one. Or, in general, it could be a face, but, usually it's been a facet so far. Maybe, yeah. So can you chase those objects? So the complexity is now controlled. It's not like I can give you any convex body now. These are all faces of this given polytope. For multi-server chasing, there are some results known in that same paper. Can we give more general results? For well-conditioned functions, can we do something? But in general, can we understand this interplay better between this convex geometry and online optimization and also online learning? In fact, what can we use this for? What can we use these body chasing results? There's a nice paper, again, of Bubeck and others. I'm afraid I don't remember all the names, where they use this to get better algorithms for online convex optimization, regret minimization. It's a smart connection. It's a very interesting connection. Are there more such connections? I believe there should be. We're starting to understand it now. So good. So that's pretty much it.
Thank you. Maybe if we have some quick question. So Ilan Cohn asks if there are lower bounds for memory-less algorithms.
Good. So there are some lower bounds for memory-less algorithms. One has to define memory-less and how much memory is memory-less. So in general, there are lower bounds for memory-less algorithms. And if you look at this SODA 2020 paper by Bubeck, Klartag and company, they'll give you some results. I don't remember them off the top of my head.
So maybe we can divert further questions to the Slack. Oh, there's one more. Are there, Jason Lee, are there any connections to online discrepancy minimization?
None that I know of.
And so the motivation is, it states like, because they're both fundamental geometric online problems. So, yes.
Yeah. Not that I know of. I mean, possibly it could be possible to phrase discrepancy minimization as some kind of chasing some kind of convex body, but I don't quite know. I'd have to think about that.
Okay, so this is the last one I will take. Musayan Bhattacharya. Are beta bounds known in the random order arrival model?
Good. Nothing's known in the random order arrival model, so the stage is yours.
I see. Okay, so let's have further questions maybe in this Slack channel, and I don't know, maybe Anupam, can you look at it and maybe
absolutely, I'll log in right now.
Okay, and then we can move on. So thanks, Anupam, again.